Okay. Okay. Okay, we got some people on here. 3 people are in. If you're here for a question that you want to ask me or just want to say hi, that's cool. Otherwise, I'm not sure I can figure out who these people are anyway. There must be a way. But anyway, if you're just hanging out, just watching, seeing what's going to happen, I'm going to do some physics problems. That's my plan, and I'll post those later. And the physics problems I'm going to do, assuming nobody is asking me a question or saying hi even, I'm going to do some AP Physics problems for AP Physics C, electricity and magnetism, as helping with our review for getting ready for the exam. So if we got no questions, I'm using the 2012 public practice exam available online, and I'm going to answer the questions. So let's take a look. Question 1 asks, a proton moving along the positive x direction enters an electric field that is directed along the positive y-axis. So what is the direction of the electric force acting on the proton after it enters the electric field? Okay, so we can make a little drawing to kind of illustrate what's happening there. So we've got a proton moving, so just we'll put down a coordinate system. So here's our coordinate system. It's y, and here's x. And we've got a proton scooching along in this direction. Okay, there we go. It's moving along the positive x-axis and goes into an electric field that's directed along the positive y-axis. So let's put that in. We're going to use blue for that, maybe. So we have an electric field in this direction. Electric field. There we go. And they're hoping you're going to screw this up by remembering magnetism. But the electric field exerts a force in the same direction as the field points for a proton. So that means, of course, that as this proton now enters this field, oh, there it is. It's got initial speed in that direction. It doesn't really matter which direction it's moving because the force will be up. Let's use another color for that. So here we go. Force the same direction because it's in a proton, and protons experience forces the same direction as the electric field. That means the correct answer is positive y-axis, which is D. F in plus y direction, which is answer D. That was for question 1. There we go. Hi, Billy. How you doing? Did you have a question about 7th grade physics, Billy? Or are you just saying hi and hanging out? It's cool too. Yeah, I'm doing well. I'm doing well. You hanging out or you got a question? Okay, cool. So if you want to just watch me do physics problems, you can do that. And if you come up with a question that you'd like to ask about our work, that's cool too. Or if you want something reviewed, that's happy times as well. Okay, so I'll keep going. So question 2 on the test is about 3 charges. And I'll just show you the problem here. There's the question 2 through 4. And the first one, first we got to draw this picture. So we're going to replicate the picture here. We've got plus Q here, big Q. Then we've got plus little q here. And we've got a minus Q down here. There we go. And the whole thing is equilateral, meaning all sides have the same length. A, oopsie. A, there we go. And they're asking several questions here. Let's take a look. The first question is, the net force on the particle with charge plus little q, this particle right here, what's its situation? Is in what direction? Good. So let's figure this out. We can draw the forces in. The plus q charge down here and the little plus q charge there. Well, like charges repel. So it's going to push this charge in this direction. Whoopsie, that's kind of crooked. We'll straighten that out. Pushes this charge in that direction. Good. That's F left charge on little q. Okay? And now let's take a look at this charge down here. The minus big Q charge exerts also force on the little charge here. And because they're opposite signs, opposites attract. So this means this exerts a force in this direction. Now, is this force equal in magnitude? Yes, it is. Why is it equal in magnitude? Because these charges are equal in magnitude and they're the same distance away from each other. So therefore, the forces have the same magnitude, but they point opposite directions. Now, pulling in this direction and pushing in that direction together, that means that the net force will be in that direction, F net. So this is F right force, a charge on little q, and therefore the net force is to the right. And that is answer C. Yay! And we're very happy about that. That's answer C. Good. Let's keep looking. Now they're asking not just for the direction, but they're asking for how much force there is. So we're asking for the amount of force. This is the direction. And then for part 3, they're looking for F net magnitude. Well, let's think about this. Looking at this diagram, F net magnitude is going to be equal to twice, because there's 2 of these. 2 of these together. And how long is one of these? Well, let's take a look. This one's 60 degrees. This one is 60 degrees. So this length right here is cosine 60 times the magnitude of that. Now, cosine 60 happens to be a half. Good. Cosine 60 is a half. And the magnitude of this arrow here, well, that's just Coulomb's law. Well, Coulomb's law says K times little q times big Q divided by the distance squared, which is a squared. We got 2, we got a half, cancel those out. Good. So that means we've got a net force of K, Q, big Q over a squared. And we're going to check our sheet to see if that's a possibility. And it's, wow, awkward. due to the other two charges. Wait, is the solution not here? Oh, they're tricking us. Oh, yeah. Okay, so part E is actually our correct answer, but they're leaving cosine 60 in there. How goofy is that? Wait, where's it? It's showing up over here. There we go. So if you look at question E, E has cosine 60 in it. Well, that's just a half, and that cancels out the 2. So E should be the correct answer. I don't like that. But, oh well. That's what they did to us. Not too happy about that. I think that's a weird way of asking that question. I mean, giving us the answers there. But, oh well. Good. Let's take a look. We've got question 2, question 3. Question 1 is answered. Let's take a look at question 4. Question 4 is using still the same diagram, the triangle, and we're looking at now potential energy. So we're asking now for the potential energy of this charge. And really, technically, that's not asked correctly because the potential energy of this charge is not even a thing. The potential energy is always resting with a pair. So this pair has energy, this pair has energy, and this pair has energy. So there are 3 pairs that together have energy, but they're asking for the energy that's associated with the little charge plus Q plus little q. Therefore, it's just going to be the top 2 pairs that we're interested in. So U associated with plus Q, we're going to do it this way. Potential energy, well, that's equal to U plus Q plus big Q plus U plus Q minus Q. Well, hello, that's interesting. Because if you look at these pairs, they have the same distance, A, they have the same magnitudes of charges, but there's a sign difference here, okay? So it means that the potential energy due to this pair over here, according to our equation for potential energy of 2 charges, K, Q1, Q2, divided by R, the distance between them, this pair is big Q, little q times K divided by A. Well, this one has the same thing, except that you have plus Q and minus Q, which means, of course, that this potential energy is the exact opposite of this one, and therefore the total potential energy will be 0. Now, you might say, and we can write that out if you want to, be K Q times big Q divided by A plus K little q times minus Q divided by A, and that's equal to 0. You might ask, well, how about the direction? Does the direction matter? Okay, well, potential energy, oh, is this potential energy like this direction? No, potential energy doesn't have a direction. It's not a vector, it's a scalar. So that means, no, we don't have to factor in which directions they're pointing because potential energies do not have directions. Okay, so there's the answer to that, and 0 for problem 4 is answer A. There we go. And that brings us to question 4A, and we've answered the first 4 questions, which are all in the realm of what's going to be on the exam. So let's erase this and start over with questions on the second page. I should have taken a picture, but I didn't. Whoopsie. There we go. Moving along. So we're now on page 2 of the multiple choice exam. We're going to clip it up a little bit, take a look. There we go. Okay, come on. Okay, so question 5. All the following statements about an isolated solid charged conductor are correct, except what? Okay, so we have a solid charged conductor. And again, they're not telling you what it looks like. So just imagine it's some specific thing, like a sphere, okay? And it's solid. Solid conducting sphere with a charge. Now, we know what happens. Okay, you have a solid metal sphere. That means that the charges pile onto the surface. Okay, inside the electric field is 0. Electric field is equal to minus dV dr. Okay, and that means, of course, if E is 0 inside, that also means that V is constant, because there can't be a change in V if electric field is 0. Okay, so those are all things we just stated stuff, and now let's look at our list, and we can see what they've got. All parts of the conductors are at the same potential. Yes, that's true. V is constant. All excess charge resides on the outer surface. That's true. The net charge enclosed by any surface lying entirely within the conductor must equal 0. Yes, correct. D, the electric field E just outside the conductor is directed parallel to the surface. Well, that's nonsense. And we can kind of picture this already like this. In this situation, in general, that electric field will look radial like that. Now, you might say, well, what if it's a different shape? Well, first of all, they didn't tell us that it's not a sphere. So statement D is definitely wrong because the electric field is not parallel. Okay, but in general, it's true that electric fields at surfaces of conductors are perpendicular to the surface. They cannot have a component parallel to the surface because that electric field parallel to the surface would move a charge. Okay, and we are in equilibrium, so that won't be the case. And it settles in a certain configuration, and in that configuration, at the surface, E is perpendicular to the surface. Period. That's it. So that's definitely the wrong answer. So D is the correct wrong answer. So D is the one we should circle for question 5. Good. So let's keep a look. So question 6 is going to be magnetic force. So we're skipping that. 7 is also skipping. And 8 is also skipping. So 6 through 8 are all with magnetism, so we're skipping those. Question 9 is magnetism. Whoopsie, maybe I'll just keep this number. So we'll skip that one as well. Question 10 is a capacitor, so we can look at those. So question 10 is a capacitor. Specifically, we have 3 different capacitors. Okay, so we have a capacitor like this. We have one like this. I'm not going to draw it, though. Maybe I am. Okay, so here's the capacitor. There we go. Boop, boop. And then we have the other plate down here. Boop, 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 boop. That's pretty nice. A, and this is D apart. So we have A and D. Capacitor 2, I'm just going to say 2D and A. And here we have D and 2A. So those are our 3 capacitors that we have, and they're going to ask questions about them for questions 10 and 11. Okay, so if we want to draw it out, this one's further apart but the same size. This one's same distance but twice as big. So you have options here. Oh, let's just draw it. What the heck? Okay, so we have this one here, same shape. Okay, but it's further apart. Yeah. Okay, this one is the twice the area, but the same distance as the first one. Okay, this is D, 2D, A, 2A. Okay, now let's take a look what they got here. So we have all these capacitors. We have charge plus Q on the top plate, charge minus Q on the bottom plate. And which of the following is true of the potential difference across the plates of the 3 capacitors? All right, so we have plus Q up here, minus Q down there. Now, okay, well, we know how this works. We have Q. This is, I call the shopping channel equation. Delta V times C, because QVC is a shopping channel. So they're asking here about the potential difference. The potential difference is delta V, and delta V equals Q divided by C. Now, they all have the same Q, so the capacitances is the difference, okay? And here's the equation for capacitance, just a reminder. You have, if it is air or vacuum, doesn't matter, then we have epsilon 0 as a variable. Then area, more area means more capacitance, and more distance means less capacitance. Now watch out, this is D, and they reuse D in here, so we got to be careful there. So let's call this one capacitance C with A over D. This one has A over 2D, right? So that means it has lower capacitance, and this is C over 2. And then this one has twice the area, same distance, so this has twice the capacitance. Okay, so let's take a look. For the potential difference at the same charge, the biggest capacitance will have the lowest potential difference. Okay, so that means that this guy will have the lowest potential difference, medium potential difference, and this will have the biggest potential difference. So 2 has the biggest potential difference, and that would be answer B, 10B. Okay. Hope that made sense. Now, let's look at the next question. The next question says, suppose all 3 capacitors are connected in parallel with a 9-volt battery. Okay, so we're applying 9 volts to each one of them. Okay, all right. And now we're asking for the electric field between the plates. Okay, now electric field, in this context for this kind of thing, is that the voltage difference is equal to minus E times D. I call it the ED equation, okay? And because it's a constant electric field, and just a reminder that E is equal to, the vector is equal to minus dV dr r. Okay, hang on a second, I'm off the screen here. There we go. So this is the equation we have, and for a constant electric field, okay, that means that the potential change is constant, and we can just integrate that easily and get that delta V is minus ED. Okay, well, what does that mean? That means if the potential difference is the same, the electric field for a small distance is big, and the electric field for a big difference is small. So that means in our case, because this is D and this is D and this is 2D, that means in 1 and 3, they have the same potential, and in 2, it has a they all have the same potential, but in 1 and 3, they have the same electric field because D is the same. And for situation 2, because the distance is 2D, that means it has actually half the electric field. So this is half the electric field of 3 and 1. So that means it is greatest for 1 and 3. It is the same for 1 and 3 and least for 2. That's answer D, and that is correct. Good. Now, 12 is, okay, 12 is actually okay, and then we can actually wipe the board. Hope you got that so far. And maybe I should take a picture this time, even though I erased the first one. At least I can post the picture maybe later. Anybody else show up? Nope, nobody showing up. Okay, that's fine. Okay, so there we go. I'm gonna erase the board and then we keep going. Can we get this done? We got 20 minutes. So here we go. Click this up. There we go. All right, keep going. So let's take a look. Now, question 12. Cool. Question 12 says, the electric potential along an x-axis is given by the expression V is equal to AX minus BX squared, where A and B are constants. At what point on the x-axis is the electric field 0? So, okay, well, we know that electric field is equal to, and we're just looking at the axis, okay? So that means that it's equal to minus dV dx, okay? All right, so that means we can find actually the electric field, and that would be minus A minus 2BX, okay? That's just taking the derivative. And of course, if we want to set that equal to 0, that can only be 0 if A minus 2BX equals 0. So that means that X is going to be equal to A over 2B, A divided by 2B. There we go. And that is answer B. There we go. Now, scooching along, question 12. Question 13 is a magnetic field question. So we can skip that. And moving along. 14. Question 14 asks about two spheres that are connected. Okay, so we have a sphere here, and we have a sphere there, and this one's the smaller radius, R2. Oopsie. R2, and this is radius R1, and they do connect them by cable, and they are metal spheres. So we have a charge on here of Q, and then this one's uncharged, and we connected, and this is supposed to be a long distance, so they don't affect each other. So let's think about this. In order for this to work, once they're connected, they form one metal object. Okay, we kind of like looked at that earlier. Well, one metal object, the entire surface will have the same potential, because otherwise charges won't flow in order to equalize that potential difference. Okay, so we have the constant potential all around. So V is going to be constant. And of course, that means in this direction, charge moves, charge flows until V is constant. Okay, we get the same potential over the whole thing. Now, what does that mean? Figure out the exact amount, but let's see the options they have here. Okay, charges on their surfaces of equal magnitude and the same sign. Well, that's nonsense. They're not going to have equal magnitude because they're obviously going to be more charge on the bigger sphere. Charges on their surface of equal magnitude and opposite sign, that's dumber. C, equal electric fields at their surfaces, that's crap. And D, equal capacitances, what? That's just a capacitance is a property of an object, and obviously a large sphere will have a larger capacitance than a small sphere. That's dumb. And then equal electric potentials is part E, so E is correct. All right, that's question 14. Good, moving along. So 15, a negatively charged conductor attracts a second object. The second object would be which of the following? Okay. All right. So we have a negatively charged conductor. All right. Doesn't matter. We have something negative attracting a second object. So we have, for example, a metal sphere, and it's attracting an object. Well, what could that be? It would attract a positive object, of course, but it could also attract an uncharged object. And let me explain. This negative charge will take the charges on here and separate them. So it will push the negatives here, and I'll put positives here, and then this object would also be attracted. So either a positively charged object or a neutral object could also be attracted. Let's take a look. A negatively charged, a conductor with positive net charge, that would work. A conductor with zero net charge, no, that doesn't really work. Anyway, it does work. Sorry, of course, it doesn't matter whether it's a conductor or not. So it doesn't matter whether this is a conductor. If it's a conductor, the pluses will really separate to the two sides. And if we have an insulator, the charges will just kind of turn and rearrange, but they will still be attracted. So this is really 2 and 3, depending on whether it's a conductor or an insulator. So either option works. So 1, 2, and 3 are options. So that would be answer E, and that is correct. Okay, and we're now on number 15. We're making good progress. We'll take a picture of that screen, and then we'll move along. Okay, we're going to erase this. We're going to move to question 16. Okay, question 16 talks about resistors. It has 3 resistors, 3, 6, and 9 ohms, and they're connected in parallel with a 10-volt battery. Okay, so we have a battery here, it's 10 volts. And we got 3 resistors connected to it. And 3 ohms, 6 ohms, 9 ohms. That's our circuit, and we could find out a bunch of different stuff about this. Let's see what they're asking. Okay, so as you know, the smaller resistor is going to get more current. So this would be, in this case, 10 over 3 amps. This would be 10 over 6 amps, 10 over 6 amps, and this would be 10 over 9 amps. Okay, or about 1.1, 1.7, and 3.3 amps. Okay, the voltage drops are all going to be the same. Across each of them is going to be 10 volts. Let's see what they got for us. So the current in the 9 ohm resistor is 3 times the current, it's 10 volts. The power dissipated in the 9 ohm resistor is greater than the power dissipated in either of the other 2 resistors. Okay, now there's different ways of looking at this, and you can get easily confused about this because you can be like, oh, I remember if you have more resistance, then you get more power, right? So just remind ourselves, P is equal to I delta V, and delta V is equal to I times R, Ohm's law and the power relationship. If we combine those, we get P is equal to I squared times R, and P is equal to delta V squared divided by R. So if they have the same voltage, which they do, 10 volts, actually the largest resistor, 9 ohms, has the smallest power. In this case, 100 divided by 9, that would be about 11 watts. Whereas this guy over here, 100 divided by 3 has 33 watts. And this guy has 100 divided by 6 is 17 watts. Okay, so looking at it from here, largest resistance, smallest power, or you can actually work it out quickly and get to the conclusion that that's a bunch of baloney. That's not true. So potential difference is the same. 16, the correct answer is B. Okay, moving along. Question 17. When 2 resistors having resistances R1 and R2 are connected in parallel, the equivalent resistance of the combination is 10 ohms. Which of the following statements about the resistances is true? Okay, okay, here we go. 17, we have another parallel resistor. So we've got this here. There we go. We got this. We got this. Good. And this one is something. This is something. And the whole thing together, our total equals 10 ohms. Okay, well, that means, of course, that we could, for example, have 20 and 20. That would work. Okay, the key thing being that the overall resistance of a parallel setup, like we have here, is always less than each individual resistor. Okay, so we had 20 and 20, that works because they're both bigger than 10. Okay, the exact numbers we're not sure, but let's see what they have. Both R1 and R2 are greater than 10 ohms. Well, thank you. That's the first answer, and that's true. Okay. 17A, we're not even going to read the rest of the question possibilities because they're wrong. Okay, question 18. Moving along. We got 10 minutes. Can we get through the 35 questions? Well, maybe we'll hit a bunch magnetic field ones, and then we can scooch along. 18. Let's squeeze 18 here. I hope we can get that done because I'm a little low. Maybe I'm going to move down. So 18, let's take a look. We've got a charge minus Q, and we have a charge minus Q here, and they are L apart. And let's see what they're asking. Two particles, each with charge minus Q, are fixed a distance L apart as shown above. Each particle experiences a net electric force F. Well, no doubt, they're going to be equal and opposite because of Newton's third law. A particle with a charge plus Q is now fixed midway between the original two particles. As a result, the net electric force experienced by each negatively charged particle is reduced to F over 2. The value of Q is what? Okay, all right. Man, so they really don't like you very much. Okay, so F is equal to KQ squared over L squared. Okay, and now they put a little charge in here, and it's going to be minus Q. Whoa, wait, plus Q, plus Q. Okay, and what that does is it reduces the amount of force that this guy experiences by a factor of 2. Okay, which means, of course, that this guy's attracting this guy, repelling this guy. This guy is attracting this guy with half of F2. Okay, which means that F over 2 is equal to KQ times little q over L divided by 2 squared. I'm even scooching out of the graph. Here we go. There we are. So those two things are true. Okay, and we can just take F and plug it in there. I'm not going to do ninja math because I think you're going to be confused enough as it is. But if we do this, we get KQ squared divided by 2L squared. And on the right side, we get all this crap here. We get KQ little q divided by L squared over 4. Okay, good. So let's take a look. The k's cancel. One of the big q's cancels. The L squareds cancel. Okay, what are we left for? Q divided by 1/4 is equal to 4Q. So on the right side, we have 4 little q. And on the left side, we have Q divided by 2. There we go. And now we can get that solved. And they specifically would like to know what is little q equal to. So little q is equal to big Q divided by 8. Now, aren't we smart? We got that done. So realistically, Q over 8, that would be answer D. I think most students are going to get smoked by that question, just so you know. I think that's a little bit tricky, and I don't know what the passing rate was on that, but I think it's going to be quite high. It'd be ironic if I got it wrong, but I didn't. I got it right. Okay, good. So let me take a picture of that, and I will also post that later. Okay, good. And I'll erase that. How are we doing on time? We got 6 minutes left. Did anybody show up? Different person that's still waiting for a question and being shy about it? If you didn't, that's okay. Okie dokie. So let's take a look. We're now on question 19. And question 19 does have a diagram associated with it. So I'm just going to hold that up right there. There we go. Good. Two objects on a horizontal frictionless surface. We're looking down on this. This is question 19. So down, viewing down. Okay. we've got a charge here, plus Q. We've got another charge over here, plus Q. And we kind of put a coordinate system in here. This is the y-axis. This is the x-axis. This distance right here is little d. This distance right here is little d. And that's it. We're looking down on this. We see two charges like that. Two objects on a horizontal frictionless surface each have charge plus q, and each are fixed in place on the x-axis at the same distance d from the origin as shown in the figure above. A particle of charge minus q, constrained to move along the y-axis, is released from rest. Oh, we put the particle up here. Okay, this is minus q. So the question is, it's constrained to stay on the y-axis, but what is it going to do? Well, let's think about it. At this time, it's attracted downward and downward. So the net force is going to be down, F total. And you might think, oh, I get it. It's just going to keep going straight down. Problem is, as it gets to the middle, at the center, if we now think about this in the center position, so the blue position, once the charge is here, now it is moving downwards. It has forces acting on it that are exactly opposite. So the net force at that point would be 0. Okay? And then later on, when it's moving over here, ah, crap, this didn't work. Chuck this. Need a green pen that works. Okay, so we're down here. We're still moving downwards at some speed, but guess what? The force from here goes that way, force from there goes that way. So the net force is actually back. So that means at this point, it's slowing down. So speed up, speed up, speed up, no force, slow down, slow down, slow down, slow down, stop. And it's going to repeat the process and oscillate back and forth. Okay, so this is kind of a really sneaky little problem. We did do this, I think, in class. I don't remember exactly, but we will get an oscillatory motion here. I don't know if might not be simple harmonic motion, but it's definitely an oscillation. So 19, therefore, the answer is B, is the correct answer. Oscillatory motion at that point. Okay, good. Now, let's take a look. Almost done. So let's look at problem number 20. Problem 20 says, a uniform electric field, E, exists between the two large oppositely charged plates shown above. So we have basically a capacitor, kind of. There we go. With a positive and a negative charge. Okay, so we have there, left is positive, right is negative, and our electric field looks like this. So there we go. And let's see what they're going to ask us. Uniform electric field exists between the two large oppositely charged plates shown above. If the distance between the plates is increased without changing the charges on the plates, which of the following statements can be justified? So we're going to keep this charge here plus Q, and we're going to keep this charge here minus Q. And we're going to increase the distance here. So we're going to move this thing over, and let's just take a look at our two equations. We have Q is equal to delta V times C, the shopping channel equation, and we have that the capacitance is equal to epsilon naught A divided by D. So D becomes larger, capacitance has to go down. So capacitance will decrease. Well, if C decreases and Q stays the same, well, that means that delta V needs to increase in order to compensate for the smaller capacitance and the charge staying constant. Take a look what we have. Electric field strength decreases. The electric field strength increases. The potential difference between the plates decreases. The potential difference between the plates increases. Oh, wait, that's what we just said. D, the potential difference increases. That's interesting. We learned something different here too. If the potential difference increases, but options A and B are electric field strength decreases or increases, so they must be wrong. That means the electric field is actually constant. Woo! The electric field is constant. That's true. And that's another way of looking at this. We can think about this as delta V for capacitors minus E times D. So if the potential difference, if the electric field is constant and D increases, delta V increases, E is constant, that's the relationship there. But anyway, this is the point here. Delta V is increasing. I might have confused you there. And that is option D. Option D on question 20. Okay, good. And that brings us to the end of my open office hours. Nobody asked any questions. That's okay. I will just post this in the AP Physics folder. And if you missed the office hours and you're in that class, you can still look at that. I will let you guys know per message that this happened. Everybody else, au revoir. I'll see you around.